Hi everyone, welcome back to the Temporal Graph Reading Group, and hope you have a great start in 2026. For today, the first talk of the year, we are very excited to host Ivan and Jacob, who will be presenting their recent paper at NeurIPS 2025 on oversquashing in spatial temporal graph neural networks. I also personally saw the poster at NeurIPS, which I find the paper to be very interesting, thus inviting them here for a talk. So I will start by speaker introduction, then I will hand the mic to our speaker today. Um, so yeah, so for our speaker today, Ivan Marisca is an affiliate researcher at the Università okay, my Italian is not very good.
Mhm.
Um, uh, della Svizzera Italiana,
It's perfect.
USI. Okay, thanks. Um, and an Alice member and the CTO of GraphSight, a Swiss startup delivering AI-powered graph-based forecasting solution for renewable energy systems. And he recently completed his PhD at um, IDSIA and USI in Lugano, Switzerland. Um, and his research focused on graph deep learning for irregular spatial temporal data, with particular interest in graph-based methods for sensory networks, including imputation, filtering, and prediction of sampled observations. He also is the co-creator of the open source ML library Torch Spatial Temporal. And if you're working on spatial temporal graph and you haven't tried out Torch Spatial Temporal yet, I would recommend you to give it a try as well. Um, and then for our second speaker today, Jacob Bamberger is a third-year PhD student at University of Oxford, working at the intersection of geometry and ML, supervised by Prof. Michael Bronstein and Prof. Xiaowen Dong. His research developed geometric methods to understand and design algorithms for learning unstructured and high-dimensional data, with a focus on graph ML and generative models. So I don't know who plan to start, but I will hand the
I
mic.
will start,
Yeah.
and then I will leave the floor to Jacob.
Okay. Cool.
Okay, so thank you, Andy, for the introduction, and thank you all for being here. So this work is the result of a joint collaboration between my university here in Lugano, Switzerland, and University of Oxford, in particular with Jacob Bamberger and Professor Michael Bronstein, which hosted me during my visit at the University of Oxford. Okay. So let's start by again. I think that many of us are familiar with the oversquashing phenomenon, which is when information is compressed and lost through the bottlenecks in GNNs, in MPNNs in general. And this is true for static GNNs already, and it has been studied a lot in this setting. But when we are instead dealing with spatiotemporal data, so where each node is associated with time series, with a time dimension in the data, this of course introduces a new additional dimension, which is the temporal one, which compounds the issue, because now we have much more data that needs to be routed in the graph and propagated in the graph. So our research question was, how does a spatiotemporal oversquashing then affect representation learning in spatiotemporal graph neural network, so STGNNs? And in this paper, what we do is that we formally characterize the spatiotemporal oversquashing phenomenon, which is a bit distinct with respect to the one in static GNNs, because as I said, there is this additional axis for information propagation, which amplifies the effects that we see in static GNNs. And what we found out is that we narrowed our analysis into convolutional STGNNs, where the temporal part is performed using causal convolutions, which is a very broad class of STGNNs. And here we discovered that basically these networks are more sensitive to information which is far apart in time. And this is a very counterintuitive behavior also with respect to what happened in graph oversquashing, where instead we think about oversquashing as something which has to deal with long range dependencies. And in order to let's say to have a trade-off of this, we also we outline some architectural modification to mitigate this imbalance when it is required. And finally, we also proved in the paper that spatiotemporal oversquashing affects to the same degree both time and space and time then models. And I will get into the details of these architectures later on. And this actually is providing theoretical support for time and space designs, which are much more scalable, because in these architectures, all the temporal dimension is processed decoupled from the graph one, and this enables efficient implementations. So we will start by introducing how information is propagating in STGNNs in general. Let's start by introducing the problem setting. So here we consider a collection of time series which are associated with relational information. So these time series are synchronous and regularly sampled. So this means that for each node in the graph and each time step, we have an observation. So we call calligraphic B the set of n time series, and we call X VT the observation vector, which is associated with node V at time step T. So here we are assuming that each node at each time step can have a vector observation, not a single value. We use this notation, so the colon notation in the subscript to indicate an interval, all the observations within an interval, where we include the end extreme. While with the capital letters, we denote the matrix of all observations, which are stacked in an interval graph. A is our adjacency matrix, which describes the relationships that exist across this time series, and in which a non-zero entry, which we also denote in this way using the parentheses and this subscript, this denotes is non-zero only if there is an edge from U to B. To give some example, you can consider, for instance, traffic networks where the space are the nodes are the sensors, traffic sensors placed in a road network, which measure the speed of vehicles. So this could be the variant of interest measured from the sensor, so the X. And the relationships can be derived from the constraints that are in the road network. But we also may think about more non-physical applications like financial markets, where each stock can be a node, and then the fluctuation of prices can be our signal of interest, and the relationships between the stocks can be, for instance, the correlations that exist between the stocks and can be modeled with our graph. Now, we consider in this work spatiotemporal GNNs, graph neural networks that can be expressed as a sequence of three operations. The first one is an encoding stage, so the encoder, in which is node-wise and time step-wise, which is simply a feature projector. So we take our input and we project it to an higher dimensional space, which is our initial representation, HVT at layer 0. Then we follow a stack of L spatiotemporal message passing layers, in which at each layer we take the whole set of representations that we have, and we exploit the relational information that we have from A, as well as the temporal information that we have. So the fact that each observation is coming one after the other, and we route, we propagate this information, and we refine the initial representations that we have HVT at each layer. And finally, we take the last layer representation associated with the last time step for each node, and we have a readout layer, which is producing our estimates of the label. So in this case, for instance, illustrated in the picture, the label is the next steps. So we are doing a forecasting task in which we want to predict the next observations for each of the time series. Importantly here, what we are not predicting a new graph, but we are predicting values of the time series. So the graph is used to condition our prediction, our estimate from the input.
Can I ask a quick question in
Yes,
tandem to
sure.
this? Like many times in applications where you know the time series have correlation, but you don't observe the graph, how would you go about kind of like learning the graph structure from the time series, from the multivariate time series?
Okay, this is an interesting question, and there are many ways of doing it. So, in some cases, like you can start from very simple approaches, such as using a Pearson correlation or very, let's say, easy to compute correlations or linear approaches that basically gives you some hint on how these the different time series might be correlated or related in general, or
Mhm.
like Granger causality approaches in which you try to understand whether another time series is helping in predicting a given time series, and so you add an edge there. There exist also graph learning methods, graph structure learning methods that start from the time series and outputs a graph. So the let's say a value, a node for each pair of nodes, telling you how likely is that the two nodes are connected.
Right, right. Okay.
So yes, you can go as deep as you want, like in terms of technical, let's say more advanced techniques, but there are also very simple techniques that sometimes are also effective.
Okay. Yeah, yeah. Thanks for the thanks for the answer.
Okay. So in this architecture, the cornerstone operator is the spatiotemporal message passing layer, so where the whole propagation is taking place. And we distinguish two classes essentially. One that we call joint space-time processing. So in these layers, basically the information can propagate across time and space jointly. So there are edges for propagation that span both dimensions simultaneously. And in these cases, for instance, a given node and time step can communicate with any other node and time step in the graph. This is an effective way to model space-time interactions, but usually it's also less efficient because we are scaling with the product of both dimensions, and also we need to design to make ad hoc designs for these equations. So another popular approach is the one of disjoining spatial and temporal processing into two steps. So at the beginning, we do a temporal processing for each node separately, and then we do spatial processing, so the message passing for each time step instead. This is nice because it's a modular and simple design, and it's also efficient. And here we can reuse all the operators we know, for instance, for any message passing layer or any what we call temporal message passing layer. But typically, this is also less expressive than a joint spacetime layer and less flexible. Some example of this temporal message passing and message passing. I mean, for the message passing, I think we don't need any introduction. For the temporal message passing, examples can be RNN or state space model in general, or TCNs, convolutional approaches in which we are conditioning the output at a given node at a given time step using a small window of past observations. But we can also have many more, such as attentional approaches and so on. Following these, let's say the inner design of a single layer, we can also consider the bigger picture and the different design paradigms that there exist for STGNets. Two are very popular. One is the most general one, the time and space approach, in which it's the most general form that we presented before. So we have this stack of spatial temporal message passing layer, And then at the end, we have a readout phase. While in the time-then space, what we do is that we start by doing the temporal processing. We have a stack of different temporal layers. And at the end, what we do is that we encode each node, the history of each node, in a single vector. And this one is later propagated, which is this ZT here. And this one is in the graph. So basically here we are reducing dramatically the computation that we have to do, because now we simply need to perform any message passing operation in a graph with static attributes, so in a single graph. It's no longer dependent on the length of the time series, the message passing stage. But this, of course, comes at the expenses of our reduced flexibility. For instance, it's tricky to handle dynamic topologies. And also an open question in the community was whether doing this decoupled approach, whether this was introducing some bottleneck or something for which, let's say, it's more difficult to grasp some dependencies. Do you still see the screen, right? Yes. Okay. Okay. Okay, going back to the oversquashing problem. So if there are some other questions about the architectures, I can take them now, or I can go ahead. Okay, I think I can go. Going back to the oversquashing problem in GNNs, a common way, a typical way that was established in recent literature is to assess the oversquashing through the Jacobian of the GNN. Here, the intuition is that the spectral norm of the GNN of the Jacobian should quantify how much the features, the initial features that we have at a given node, U, then influence the output, which the last representation, which is computed for node V at the end of the processing. And for these sensitivity analysis, there is this famous theorem from Di Giovanni and others, where considering a GNN, a broad class of GNNs with L layers for any nodes U and V, we have the spectral norm of the Jacobian is satisfying these inequalities. So it's which depends on two factors. One is dependent on the model and the other on the topology. So here this S is basically the function of our edges in the graph. So building on this insight, what we aim to do is to study the spatiotemporal oversquashing through the spectral norm instead of the Jacobian of the STGNN. And so here we are no longer interested in not only interested in how the features of another node influence the output, but also how much the features of this node, of another node U at time t minus I, how they influence the output of a node V at time step t, so I time step afterwards. And for doing so, we consider a class of architectures where in which we have L layers of spatiotemporal message passing, and these layers are of the disjoint space-time processing type that I presented before. And so we have LT temporal message passing layer followed by LS message passing layer in each of these layers. So why did we choose these approaches? Because if we then vary these parameters, so LT, LM, L, LS, and LT, we can go interpolate basically from a time and space approach to a time and space. Because here, the only important thing is the product between L and LS and LLT, which we call computational budgets. So LLS is the total number of message passing layers in our architecture, while LLT is the total number of temporal message passing architecture. And if we keep L fixed to 1, we are in the space case, because we are doing all the temporal processing before and the spatial processing afterwards. While if we take the inner layers equal to 1, we're basically constantly switching between temporal message passing and spatial message passing. And the idea for us was to then study the oversquashing, the norm of the sensitivity, so the oversquashing bound in function of this layer to see whether there was some difference and where between attainment space and time-dense space architecture. Interestingly, here in this within a layer, we can easily see that since the temporal processing is performed node-wise and the spatial processing is performed time-wise, the Jacobian for a single layer can be factorized in a spatial component. So how much which is exactly and precisely the one that we have in GNN. So how much a feature of the node V, the computed feature for node V is influenced from the input at node U, and a temporal one instead, in which we are fixed in a single node, in this case node U, and we see how much an input is sensitive to another, an output is sensitive to another time step in the input. So we narrow again our analysis and we focus on message passing temporal convolutional networks in which the temporal processing is implemented in causal convolutions with a kernel size of P. These are in these architectures, basically in TCNs, what we do is to assign a weight to the last, to the most recent P input that we have, and these values are the weights are the same in each, let's say, for each time step, the respective weights. Indeed, we can also express a solution as a matrix multiplication of the input using a Toeplitz matrix R, in which we are arranging all these filter elements in the diagonal, in this case, the lower diagonals of a matrix. All elements are set to 0. And so we can write the convolutional operation in this way. And if you think about it, this is very similar to what we have in GNNs, in convolution in general, and yes, in convolutional GNN, in which we multiply the input with a kernel, with a graph shift operator. And so here, indeed, R acts as a temporal topology matrix. So this is telling us how nodes, how time steps are connected. If we take the power of L, the element ij is exactly the number of paths that we have from t minus I to t minus j after L layers. Okay, so now we start by here, let's say this is the prototype for the message passing TCN, so the full STGNN. And since we did the decoupling before, so the coupling temporal and spatial processing within a single layer, we decided to focus on the two separately, and starting with the TCN in general to study how the oversquashing, in a sense, in a certain sense, with some abuse of notation, is happening in TCNs. So we take the spectral norm of the Jacobian that we are studying for the MP-TCN, and we start from the temporal component. So we just keep the same, the nodes fixed. And here we can see that in a, this is a theorem of the paper. And so here we can see that in a TCN with LT successive layers, all with the same kernel size, and assuming that the weights are bounded with the same, the norm of the weights are bounded with the same value W, and this the Lipschitz constant of the activation function of the TCN is this C sigma here. Then we have that for each time step, so for each leg from the last time step, we have this inequality, this bound, which is mirroring what we have in the GNN, in GNNs. So here we have the bound, which is decoupled in a model versus topology component. Okay, then this is nice, and it is also very similar to what we have with the graph, and it's not maybe not so surprising considering that basically a graph operation is a convolution in a sense, and so differently from graph here, what we have is that we know R, and R as a precise structure is not a generic graph, but is a lower triangular Toeplitz band matrix. So basically this means that after some index I, all the elements are 0. And asymptotically, if we take powers of these, we have the so-called sink effect. So for any R that basically has these properties and with a kernel size of at least 2, so which is not simply an identity kernel, we have that for any I which is greater than j, the value of r to the power of l, r to the power of l of the jth element with respect over the ith element is going to 0 as L goes to infinity. So this means that the influence that is exerted from a time step that is a J time step from in the past from a given time step is much higher with respect to another time step I, which is instead closer to the target time step, so to the present. So basically, this is telling us that counterintuitively we are overemphasizing earlier information when depth increases. And yes, this has also been referred as the sink effect. So when we are taking a high value for L, so asymptotically, the recent input vanish completely, and all the focus goes to the very first token, so to the very first time step observed. We can see also some illustrative example of this. So this is exactly what happens with TCN with kernel size 3. So we are taking the last 3 steps, and we see, and here we are seeing the exactly the bound. And so here we see that sorry, the influence. So R to the power of L each element. And here we can see that as soon as we increase the number of layers, we are shifting the focus towards the very first time step. And so mind that this is an logarithm. I mean, these are powers of the of 10. So these are very big values. And here, what we can see is that even if we are not taking many layers in our input, so maybe 30 is a lot, but also if we are around 4 or 5 layers, so in this regime, what we are doing, so it's to put much more influence and focus on time steps which are in the middle of the sequence rather than more close to the let's say last time steps, which is the one that we actually care the most. A similar behavior has also been observed in other applications, such as LLMs, or transformers in general, in which we have basically in all applications in which we have this causal aggregation. And so here, from this figure is from a paper from Barbero and others, in which they show that in LLMs, the very first token is gaining much more attention with respect to all the other in the input. So I have also an overview of the proof of this theorem, and maybe I can leave it here, or we can discuss it maybe at the end of the presentation if there are specific questions. While instead to talk more about what we can do to mitigate the of this over squashing, let's call it over squashing, or in general this sensitivity problem that we have in our input. The approach that we decided to tackle is about rewiring, in a sense, the temporal graph, just to borrow, let's say, the same terminology used in GNNs. And so one approach is also, which is also what has been done in for other reasons in deep learning for time series, is to use dilated convolutions. So here, instead of what we're saying is, instead of always taking the last k, the last p elements at each layer, we dilute the kernel so that we take one every p, for instance, p to the power of l can be a strategy. And basically, in this way, we are exponentially expanding the receptive field, but this also reduces the number of paths that we have from earlier tokens. So if we consider the plot here, the very last time step has exactly the same number of paths to the output with respect to a time step coming before. And this is valid for all the time steps here. So basically, what we are saying here is that to every input time step has exactly the same strength in influencing the prediction for this last token. And this is maybe desirable in some applications, but also what happens is that after a few layers, which is since this is saturating, this exponential expansion is exponential, it's saturating fast, and after a few layers, we wouldn't have any more other information to gather, but only what remains is just to propagate the last layer. So in that case, what we do is to reset the dilation so that we start back again with a kernel size of this way. This actually then is reintroducing again the sync behavior, because at that point we no longer have the property of having just a single path from each node in the input. So another solution that we proposed is to row normalize the convolutions. So this means that we simply divide the input for the number of paths that are at the number of edges that are outgoing that input. So that means that for the last layer, for propagating the last time step, we use a weight which is 3 times higher in this case of all the other time steps, especially those coming at the beginning. And this allows us to converge slowly to a uniform attention distribution over the entire sequence. The drawback of this approach is that it has only effect on the last token, so the others still keep a sort of a sync behavior. But in main applications, such as the one we are interested in here, we just care about the last time step representation for our output. Here we can also see how these actually in each layer, so in the stack of layers, we can see the matrix. This is the matrix R to the power of the layer which is shown here. So in the vanilla TCN, we see that at the beginning the focus is in our let's say in the last 3 time step, but then it starts shifting towards the beginning, and as I was mentioning, this is the famous sync effect. So basically all the attention this is normalized for between 0 and 1. So this has an extremely higher impact on the prediction with respect to all the other time steps in the sequence. This is in function of the distance from t. So basically, this is the most distant time step with respect to 0, which is the closest. And we can see that with the row normalization, we have this kind of behavior, which instead the strength, the influence is is much more important. Let's say the influence is much more strong for time steps which are close to the last one. And as soon as we increase the number of layers, this focus is shifting towards the full time series. In targeted convolution, instead, we start by filling all these metrics. So as I said, everyone has a single path to a path with the same number of steps to influence the last layer. But then as soon as we do the reset, which happens at the layer 4, I guess, 5, I don't remember, 5, then we start again with the sync effect. Okay, so that's it for my side. If there are questions on these parts, I can take them now, or I can leave the floor to Jacob.
I guess, yeah, no questions. So I'll just keep going.
Okay.
Yeah. And again, feel free to interrupt me if you have questions. Great. So yeah, so this slide is about we will try to understand this behavior mathematically that Ivan just explained. So we just saw this like as you take higher and higher powers of this row normalized matrix, we saw this convergence to like you saw this the first column was much higher than the other things. And so I guess we went ahead and proved this mathematically. And indeed, if you have this row normalization, you can prove that as you take higher and higher powers, the influence of other nodes on this final time step that you're trying to predict at is equal. And so you can see this at the bottom right. You can see this with the dark green curves, which show equal influence between all other tokens, which is exactly what we wanted. And I guess we want to, and this is, yeah, again, in contrast with vanilla temporal causal convolutions and dilated ones, which won't have this behavior as you take larger and larger powers. And yeah, so theory is all great. We've talked mostly about theory of over squashing, etc. And I think generally I have the hardest time with the line of work on over squashing is that it's very hard to translate the theoretical result to practical results that matter for practical implementations. And so we tried to bridge this gap. So as a first step, we considered some synthetic tasks, which we look at here. We consider the copy first and copy last task on sequences. So here the input will be a sequence of a given length, I think here length 16. The input node features are going to be uniformly random, I guess, yeah, features between 0 and 1. And so the copy first will try to copy the very first token in the sequence, and the copy last will try to copy the very last token. And we measure performance by the success rate, which is if after training you reached a good enough performance in this regression task. And we repeated that several times and we compute the success rate. And if you look at the performance of the standard causal convolution, you'll observe that the very first, so if you look at the copy first task, so the filled in blue curve, you'll see that at the very beginning, the performance is really bad, it's 0, because the receptive field is too small to capture the task. However, once the receptive field is covered, once the task is covered, then you get 100% accuracy, and this keeps going up until very deep, even for very deep network. Right, so here, yeah, I didn't mention this, but the x-axis is the number of layers. Now, if you look at the copy last task, which intuitively should be a lot easier because all you have to do is propagate information for one hop because it's only the last token you're trying to copy. You'll notice that the performance is very good for shallow networks, but decreases very fast for later networks. And so this theory that we presented, we can observe this in practice in this very controlled setting, but it does happen, right? So, and that's quite important for theoretical work. Then, so if you look at the normalized convolution, you will have maybe a more expected behavior, right? So as we talked about, the normalized convolution will give you a more local inductive bias. And as you can see, both copy first and copy last follow the similar pattern, meaning meaning so once the receptive field is covered, the both tasks will get this similar accuracy and they will eventually drop down. So I guess for copy last, it dropped down later because, as we said, it's a local task, and this network now has a local inductive bias, and the copy first drops down earlier because it is a more long-range task, which is, in theory, should be harder for these networks. And then perhaps the best performing model is the dilation one, and this mitigates both behaviors. And I guess, this is probably due to more of a learning problem rather than not being able to solve the task because of our theory that we talked about. But
Just a
yeah,
quick naive question. So does this also mean that if you are picking hyperparameter with your temporal GNN, you should be very careful of how many layers you have, as seen from
exactly.
here, and there seems to be an optimum where it's around 5 layers or so, seem to be work best no matter what you do, like out of the three different setups, right?
Mm,
So does it kind of form some sort of practical guide for how people can choose these hyperparameters? Um,
So I guess it's very task dependent, and these are two examples of very synthetic tasks. So I guess for
mhm.
these tasks, maybe 5 layers is the best, but I wouldn't, extrapolate to any task, take 5 layers. However, it is true that these results highlight that the number of temporal layers is quite important when it comes to over squashing. And so you have to be careful with that when you pick this hyperparameter.
And then how would you imagine a copy middle task look like?
I guess copy middle. Um, so I guess it depends on what architecture. So if we take the standard architecture, I guess I guess it also depends on
It's
the
not
sequence length,
clear.
right? So
Yeah.
Mhm.
like if you were to, copy last is really copy 16 hops away because this
Yeah,
length is 16 hops. So
right.
you could just increase the sequence length and you would probably get a very similar curve to the blue curves you already have.
I
Um,
see. Okay.
yeah,
Yes, probably like in the vanilla one, you would expect it to be more easily solved in the focus is in the middle. So
Hmm.
yes, it's difficult to do a discussion in absolute terms because it depends on the sequence length for
Yeah,
sure,
yeah.
on the kernel size and all this. Yes.
But do you think that would be kind of harder than both? So I guess what I'm trying to say is that do you think that would be harder for the architecture than the copy first and copy last?
that's a good point. Actually, now that you mention this, I think there's this thing in LLMs or sequence models called lost in the middle problem.
Mm.
I don't know if you're familiar with this. And I guess that's kind of what you're referring to, where if you're trying to retrieve information that's in the middle, I think it's been observed that it's harder.
Yeah,
Yeah, yeah.
I think that one also depends on the fact that usually what we do in modern architecture is also to use skip connections and some tricks to keep your initial information. So if you
Hmm.
combine the two, so this is giving you like a very strong bias to what is coming from the beginning, or skip
Hmm.
connections are giving you a strong bias on what is recent. And so maybe that's why you can lose something in the middle because it's
Hmm.
something for which you are not giving the right inductive bias, in my opinion.
Right. That makes sense. Yeah. Thanks.
I think we can go to the next slide. Yeah. Great. So just to summarize what we've talked about until now, I guess we've introduced the spatiotemporal GNNs. We've talked a bit about oversquashing and standard MPNNs. And then we observed that there was a bit of a hole in the literature when it came to information propagation of causal convolutions. And so we went in depth into studying those. And now what we're going to do is to put everything together using the classical results on MPNNs and our new results on causal convolutions to get some formal results on MPTCNs, which are message passing temporal causal convolutional networks. Um, Great. And so what we get is not surprising. So the assumptions on this bound is the same as in the previous results. And what you'll see is a very analogous result to the standard MPNN results, meaning that the upper bound you get on this Jacobian, on the spectral norm of the Jacobian, will split into both the model component and the spatiotemporal topology. But then what's even more interesting is that in the spatiotemporal topology, it also splits between the spatial part and the temporal part. And so this gives us two observations, which is that, so we talked a lot about time-dense space architectures and time and space architectures. And what we get is that from this theoretical analysis, both of these will get the same bound on the condition that the spatial budget, so L times Ls, is the same, and the temporal budget is the same. And so this kind of, yeah, intuitively we think that time-dense space is very different than time and space, but actually from this theoretical analysis, they will be the same. And then the second observation is that it is a good thing to improve this bound, right? Like as we've seen with rewiring, like it seems to improve performance. However, now we notice that if you want to improve this bound, you can act both on the spatial part, but also on the temporal part. And so, and acting on only one might be insufficient because the other one might be bottlenecked. Yeah. And so I guess there's a bit of a proof overview. I think we're probably not going to have enough time to cover this. Maybe, yeah, I think to me this slide was interesting because you see exactly where the spatial part and the temporal part kind of splits up. And this is surprising, especially for time and space networks. But I think we won't go too much into details here, and we can
Yes,
come
maybe
to
it's
this
something else.
if people want to. Great. So yeah, so now going back to, so we've seen synthetic tasks purely in the temporal domain, and we gained some intuition. Now we're going to try to do synthetic tasks in the spatiotemporal domain. And in order to do this, then we drew from inspiration from the ring transfer task, which has been quite widely used in the standard oversquashing analysis, which essentially in a graph, you're going to want to, you have a source node and a target node, and the goal is for the target node to copy the input at the source node. And so we basically took this task and extended it to the spatial temporal case. And instead of copying, we replaced it by averaging because copying was hard to define formally, I guess. And so the task here will be at the target node, you want to output the average of the inputs at the source node at a specific timestamp, t minus p. So so this gives you kind of yeah, two hyperparameters, I guess, which is, well, I guess the source and the target, but also the timestamp p that you want to copy at. And so here, for example, I think the purple node will be the target and the green node will be the source. And we consider two topologies, again, following the literature on ring transfer. On the left, the ring topology, and on the right, the lollipop topology. And so, and essentially for these different hyperparameters, we train the standard causal convolution network to solve this task. And so we report the results in these heat maps. On the x-axis, if you look at the bottom left, on the x-axis will be the temporal distance. So that's one, how far in the temporal domain your source node is to the target. And then the y-axis will be the spatial distance, so how far apart in the graph the two nodes are. And generally, what you'll observe is that, as a standard in oversquashing, if the spatial distance is high, the task will get harder. That's why the top part of these heat maps is dark, which is 0% success rate. And however, when it's close spatially, it's going to be easier. Then if you look at the temporal part, you'll observe that oh yeah, and maybe staying on the spatial part, we also observe a big difference between the ring and the lollipop. We observe that the lollipop is generally a lot harder. And this is again consistent with the literature. It basically, if you look at the lollipop, it will have like this one big cluster. And basically it's very hard for information to exit this cluster and to go into this line graph in order to access the purple node. So that's on the spatial part. Now, if you look at the temporal part, you observe basically that when p is equal to 2, so when basically the width of the convolution is small, there is not a big difference between the different tasks. However, when you increase p, you see that the shorter distance, the shorter temporal distance will become harder, whereas the longer temporal distance will become easier, and that's again very aligned with our theory. And yeah, and then moving beyond the synthetic benchmarks, we also tried this out on real-world benchmarks. So first, we wanted to test. So basically, from our theory, we saw that the bound was the same for time and space architecture and the time-dense space. So the first thing we wanted to test was, so which one performs better in practice? Is it time-dense space or time and space? And maybe surprisingly, so if you look at, so we tested this on 3 benchmarks, and maybe surprisingly, if you look at the top right 9 entries, you'll observe that the time-dense space, overall, I guess, yeah, so each line will be a different value of big L, which is kind of the outer loop. So when big L is equal to 1, it's a time-dense space. And what we observe is that often the time-dense space will outperform the time and space approach, which was kind of surprising because they are easier, they are simpler, and they are faster, and have a smaller memory footprint. So then we wanted to test what we proposed, which is this row normalized convolution. And so we tested this on also for the different values of L, and we observed that generally it's very comparable to without row normalization. However, we observed that there is a big difference in this NRAD, where we get very, very good results with this row normalization, suggesting that actually in some cases it can improve accuracy. And then finally, we took a very sophisticated architecture that does very well on these benchmarks, which is this graphite. And in its original formulation, it's a time and space approach. And what we did was to change this into this time-dense space approach. And we observed very little performance drop, and in some cases even improved performance. And we see that actually this what we obtained from the theory seems to remain valid even for these more sophisticated architectures. Yeah, and then as another ablation, we also saw, I guess in the theory, we thought that this bound we got split into the temporal domain and the spatial domain. So we wanted to investigate what is most important, and can helping in the temporal domain and in the spatial domain, can that compound and give us a better performance? And so we tested this on one of the benchmarks, and the results gave us that both methods actually improve. So yeah, we considered this first order spectral rewiring, and we saw that doing spatial rewiring or temporal rewiring improved in both cases, and the best performance was reached when we did both. And in fact, and this was kind of surprising, we found that actually in this case, the temporal rewiring was a lot better than the spatial one. And so, yeah, I guess the takeaway is that it's important to look at both forms of oversquashing in designing these architectures. Great. And so a couple of concluding points. So yeah, we provided a formal characterization of spatiotemporal oversquashing in STGNNs. Then we saw that the temporal dimension introduces an additional bottleneck, which gives some counterintuitive amplification of long-range temporal dependencies in convolutional models. Then we saw that under our theoretical analysis, the time and space and time-dense space architectures are equivalent. They give the same bounds. However, I think it's really important to question the assumptions of these analyses. So this is maybe to take with a bit of a grain of salt. And we did some experiments and in order to confirm our theory, both in synthetic cases and in real world cases. And as future directions, I think, yeah, so the class of architectures we consider is somewhat limited. We looked, it doesn't cover all possible STGNN architectures, so there's still work to do in order to understand the joint spacetime STGNNs and recurrent STGNNs. And then I think this in general, over squashing is great. It gives us bounds and it gives us intuition. But these bounds are loose and they can probably be improved. So it would be great to derive tighter data-dependent sensitivity analysis. And finally, yeah, I guess future direction will also include rewiring to systematically study rewiring and normalization strategies for mitigating oversquashing. Great. Yeah, and I guess, yeah, thank you to all the collaborators. Thank you to everyone for being here and for listening. If you have any questions, now's the time.
Yeah, thanks for the great talk. I do have questions, but maybe I will leave it for the audience to ask questions since I've been asking all the questions. Um, so from the audience, if you have any questions, feel free to type in the chat or just unmute yourself to ask. Yeah, so definitely a very interesting talk. Um, so I think, oh, so I guess I will start with the questions and then people can type their questions and so on. Um, but I think, so in my head, fundamentally, when you are learning a dependency over, so again, I'm not expert, but when you're learning dependency over the spatial temporal graph, you basically, so if we think about all the space of information we can contribute to a prediction at the current time, it's essentially a third order tensor, and you are essentially learning what you want to do to find the optimum function is you need to learn to pull over information from the past through this third order tensor from the correct space of things to pull over that and then to result in the prediction. So the function that you learn to do that is kind of like you are learning like which of the path that can get to this point is the most influence. And I think like spatial temporal GNNs do that already, but I think it's also like simplifying because you are having a GNN and the temporal part, and they kind of only model them kind of somewhat disjointly, but not as and so potentially yeah, not very clear in my head. It's just some idea as I was like thinking about.
Yeah. Do you want to take
Yeah,
this?
yes, I can go on. First of all, thanks everyone for being still here and for listening to the talk. And about your question, Andy, yes, so this is kind of related to what we were discussing before about the joint processing and this joint one. So you can have also, there are actually SDGNNs in which you model directly the product graph, let's say between the space and time, the spatial and temporal graph. So in that sense, what you have is that the tensor, the three-dimensional tensor you were mentioning with the space, time, and features, and you have edges directly modeling information propagation across these three dimensions, or just the two space and time dimensions.
Right.
In my opinion, what I think is that what I observed, let's say, during this journey is that the decoupled approach that intuitively one may think to be inherently limited and that might introduce some bottleneck, then actually I mean, these applications are also very often like short-term forecasting or classification or something which is maybe which doesn't need a lot of information. But in these settings, I noticed that these joint approaches are working very well. Probably because, again, the information you actually need for your forecast is not maybe that spread out in your input. And so if you do something like that, it's already it's already enough.
Mm-hmm.
But maybe there are applications in which instead modeling precisely and more with more expressivity, some edge that span this dimension is maybe more helpful. I mean, at the end of the day, what we do is to introduce inductive biases in how to gather this information from these third order tensor that you were mentioning. And so, depending on applications, you might think that this tensor is too big for you, that you don't really need much more of this information, but just focus on something which is local. And there, I think that an approach like this one is working very well. But if you already know that the information that you have to take into account is spread out, is a lot with respect to like the density of information is a lot in this tensor, probably is not a good approach.
Right. That makes sense. This, as you mentioned, could be a data dependent thing. So this could be that we are still mostly training with single data sets for a specific task. So then maybe if you want a more general model, then maybe you need more expressiveness to kind of pull over an arbitrary function over this 3D tensor that you can put attention to.
Yes. Yes, I think that's like, for instance, in foundation models, I think that these techniques are probably more useful, or this discussion in general,
Sounds good.
which I think also is the direction that we are taking probably as a community, going towards foundation models or to train big models in much bigger data sets and in broader scope.
Yeah, for sure. Yeah, so that's my main question. Yeah, so thanks everyone for the talk, and thanks to the speaker for the talk. Thanks everyone for staying at the talk. And since we are over time, maybe we'll like wrap up here. Yeah, and thanks for the super nice slides. The visualizations were pretty cool as well.
Thank you. Let
So
me simply go through the references so that they remain for the
Legal
recording,
reasons.
maybe.
yeah, for the recording, yes, yes, sounds good.
Okay.
Okay, perfect. Yeah, thanks everyone.
Okay. Thanks.